preparations for the last servicing mission to the Hubble Space Telescope are well underway at several NASA facilities. Almost all 22,000 pounds of Service Mission 4 hardware is at some stage of integration and test at the Goddard Space Flight Center in Maryland. This includes new gyros, batteries, fine guidance sensor, astronaut tools, support hardware, a new docking ring, the carrier systems, and 2 new Hubble science instruments. The Wide Field Camera 3 begins its third and final thermal vacuum test shortly, where it will experience the harshness of space inside a large simulator for several weeks. The Service Mission 4 astronauts come to Goddard to practice installing the camera into the Hubble Space Telescope high-fidelity mechanical simulator, as well as the carrier systems that will transport the camera to orbit on board the space shuttle. The Wide Field Camera 3 will be Hubble's most advanced camera, increasing its discovery efficiency by a factor of 5. The Cosmic Origin Spectrograph, a point-source ultraviolet spectrograph, is ready for flight. Astronauts practice installing COS into the high-fidelity mechanical simulator and the carrier systems. At Goddard, engineers and astronauts work together developing tools and techniques to resurrect 2 malfunctioning science instruments currently on orbit inside Hubble. Both the Space Telescope Imaging Spectrograph and the Advanced Camera for Surveys suffered power supply failures. This is the first time a repair like this has ever been done on orbit. One of NASA's premier training facilities at the Johnson Space Center in Houston is the Neutral Buoyancy Laboratory. In this 6.2 million-gallon swimming pool, Goddard engineers work alongside the astronauts as they train for the mission. Scientists and engineers are excited about flying this last servicing mission to the Hubble Space Telescope, and will update you periodically as preparations continue.
My team builds a variety of tools, anywhere from power tools to different hand tools that the astronauts will use. The biggest challenge for us in designing and developing tools for astronauts is to make it easy for them to use in their suit, and especially with their gloved hands that fatigue easily when they're working on orbit. Our team is called the Crew Aids and Tools. It's not all just tools. We also build different things that aid the astronauts in doing the task. We build all the handling aids for any of the instruments or to transport the or use the orbital replacement units when they're doing the changeouts. EVA time is at a premium, so any tool that we develop it in order to optimize the time that we have up there and make it as easy and simple for the astronauts to use.
We develop tools for HST. One could think you could go to the hardware store and actually pick out a tool and use that and just deliver it with the astronaut to use in space. The space environment is very harsh. It's very hot, very cold, and it's also in a vacuum. And most tools, power tools for example, that you pick up from Home Depot, just would not survive in the environment of space.
The repair task for this one instrument that's about the size of a refrigerator, we call it STIS, but STIS is an acronym for Space Telescope Imaging Spectrograph. And that task is a little bit different than what we normally do. In this case with STIS, we don't have a replacement module for it. So what we're going to do is we're going to try to replace a card that has failed inside of the box.
To actually open up an instrument and pull a board had never been thought of nor conceived that we would want to do that, and therefore the interfaces were not very friendly to an astronaut.
In fact, there's 110 of these very small screws that we need to remove from the instrument in order to gain access to the board we need to replace.
The beauty of the fastener capture plate is it does capture all the fasteners, but it's got a clear window, and that clear window enables the astronaut, when he takes that power tool, he can actually see the little tiny bit going into the little tiny fastener. So we have not blocked any of his visibility, yet when he takes that fastener out, it won't come out the little hole that the tool passed through.
In August of 2004, there was a 5-volt power supply that drives the mechanisms on STIS, and it failed. When that happened, it basically meant that STIS could not do science anymore.
STIS was our first black hole hunter. It confirmed for the first time the existence of a supermassive black hole in the center of a galaxy, and it went on to make the first detection and chemical analysis of the atmosphere of a planet around another star. We want to keep on doing that kind of work.
STIS is what's called a spectrograph. What it does is spreads the light out into its different wavelengths. That's really important if we want to learn about how fast an object is moving, what it's made of, what the pressure and temperature. It's getting at the physics of what's going on up there in the universe.
You might well ask, if we're going to fly a cosmic origin spectrograph that's the most sensitive spectrograph we've ever put on Hubble, why do we need to bother to repair the Space Telescope imaging spectrograph? Space Telescope imaging spectrograph can do a number of things that COS can't do, and conversely. Between the cosmic origin spectrograph that's very fast and very efficient, and the Space Telescope imaging spectrograph that provides finer resolution and a smoother cut, as it were, through the light from a star or a galaxy, and you have a much more complete set of tools to use for a variety of purposes.
There was huge motivation to recover STIS, so our engineers embarked on one of these rapid development programs, and the STIS failure was very easily characterized. We knew exactly what happened, we knew exactly what card, we knew exactly what component, and the challenge became, can we get to it?
This particular activity that we're going to do to try to fix STIS wasn't meant to be done in space. It was meant to be done here on Earth in a clean room.
Now, since no one ever expected this to happen, when they sealed up this instrument, they sealed it up so it was nice and secure. In fact, there's 110 of these very small screws that we need to remove from the instrument in order to gain access to the board we need to replace.
And these screws are not what we call captive. In other words, as you take the screw out, it's loose. There's nothing holding it to the board. The engineers here at Goddard have been very creative in designing a cover plate that we can put on over top, that as we take the screws out, they'll be captured by this plexiglass cover.
We designed what's called the fastener capture plate. It attaches onto the instrument. It's got holes that the astronauts can access their tool into. They're small enough for the tool bit, but not large enough so the fastener can come out.
My job is going to be to drive each one of these screws, remove that plate, get inside of it, and then remove the board, much like you would remove a board in a computer in your house, except we're in these fancy clothes, a big fancy spacesuit, and we're using fancy tools to do it. We want to make sure we do it right.
If we are going to go do exploration and continue with on-orbit assembly and test of spacecraft, we got to learn how to do that. We got to learn how to pull boards out and put boards in. And so here we are, Hubble once again is the Pathfinder.
When you look in the shuttle bay for the Hubble servicing mission, you'll see these 4 large structures we call carriers. And they carry all the space flight hardware, including the scientific instruments, the brand new ones, into space to service Hubble Space Telescope.
The carriers provide the structural support and the electrical support to ensure that the instruments and electronics that we are launching on the shuttle arrive there safely and securely.
Booster ignition and liftoff.
Loads that are exerted during liftoff, the static acceleration, the random from the acoustic noise, all of that stuff is bad for electronics. And one of the things we have to do is provide load isolation so that nothing breaks before it gets up to Hubble. We provide heaters to make sure nothing gets too cold. We don't want to get too hot either. We want to be just right when it's ready to go into Hubble.
Everything's assembled at Goddard, tested here at Goddard, and then shipped down in large shipping containers and various containers to Kennedy for integration into the payload bed.
For servicing mission 4, we'll be flying with 4 carriers. The one closest to the tail is the Mule. It's carrying contingency hardware. The next one going forward is the flight support system, which is our primary berthing platform for the Hubble.
And it's also carrying a new soft capture mechanism. It's basically a ring that'll attach to the bottom of the telescope for a future rendezvous capture of the Space Telescope.
In front of that, we have the Orbital Replacement Unit carrier, which has 2 instruments in it.
The ORUC is really the workhorse carrier. It is carrying both the cosmic origin spectrograph and the fine guidance sensor. It is also carrying the ACS repair hardware, the STIS repair hardware.
The new one is up front, and it's called the SLIC, the Super Lightweight Interchangeable Carrier.
The only way we could carry up everything we wanted to take up on the very last servicing mission to Hubble was to design a new carrier system that was lightweight. SLIC is the unsung hero of the SM4 carrier systems. It is what is enabling us to take the brand new Wide Field Camera 3 to orbit. If we didn't have SLIC, Wide Field Camera 3 would not be flying to Hubble.
SLIC is actually a new technology for our space support equipment.
The SLIC carrier is a composite carrier. It's made essentially of carbon fibers instead of metal.
And the nice thing about the graphite composite is you get a lot of strength for less weight. So you have greater payload carrying capability.
Because SLIC is the first carbon composite airframe to fly on the space shuttle, we had to do some really special things.
The SLIC structure had to go through a significant testing program to prove out that it'll survive the launch and landing stresses that it's going to see. The test involved putting the carrier into several different configurations and then pushing and pulling on it with these actuators, which are just rods that push and pull on it, to simulate the stresses or loads it's going to see when it's launching and when it's landing.
All of that made us a whole lot smarter and a whole lot more experienced in the world of composites. And we're now working with the people in the exploration program to help transfer that knowledge to them so they can benefit from it.
The Wide Field Camera 3 is one of those instruments that's going to make Hubble 10 times better in discovery space. It's the highest science priority on the mission, and we're very excited to be able to put this new camera in.
We do have to take out an existing instrument that is still operational, and that is the fabulous WIFPIC 2. I mean, that has been the workhorse imager for HST for much of the HST lifetime, from its installation in the 1993 first servicing mission. It was the first camera that gave the kind of images that HST was intended to provide. So many of the iconic images like the Eagle Nebula, Pillars of Creation, and so on, those are WIFPIC 2 images.
Wide Field 3 is probably 2 generations improved over WIFPIC 2. Wide Field is what they call a facility class instrument. What they did was assemble a team of scientists, and they got together and said, let's put together the best possible instrument that can give us the widest possible scientific use.
The original design of Wide Field, the day one design of Wide Field, was very similar to WIFPIC 2 in the sense that we had a single camera. However, it was decided to add a second camera inside the wide field camera 3. We want not just great UV visible performance, we want great infrared performance. And that caused us to take the initial design, which is essentially pretty full, 5 pounds of sugar in a 5-pound bag. It all fit quite neatly. And now we had to add a second 5 pounds of sugar into this bag.
There is so much stuff inside wide field that all of our electronics boxes have to hang on the outside. And it looks a little bit like Fibber McGee's closet with harnessing and all of these wires and cables and everything's connected all funky. And it's just because they're trying to do so much with this facility class instrument. It's the last imaging instrument that's going to be put on the telescope. We want it to provide spectacular imagery.
The most novel technology, however, was the infrared arrays. The infrared is particularly good at looking at the very distant universe. And when you look at things at a great distance in astronomy, you're also looking far back in the past. So closer to the beginning of the universe, closer to the Big Bang, earlier in the lifetimes of galaxies and so on.
Because wide field camera 3 has this wide pan-chromatic color coverage, we can progress from ultraviolet to visible and then progress onward beyond that to the red and the near infrared. And as we do that, we're progressing from hot young stars to middle-aged stars to older stars within the same galaxy. And all those different populations of stars exist within the same galaxy. It's the family album, the family photo album for that galaxy.
The other thing is to probe this very mysterious phenomenon that's called dark energy, which is the catchphrase for a force that is not understood in terms of the physics, a force that is accelerating the expansion of the universe.
What's been so amazing about each of these cameras over the history of the Hubble program is what it finds is something we never knew. We point it, we learn a little bit, and somebody goes, huh, I wonder, and off they go. And then the world has changed forever based on something that we could not have imagined while we were down here on the ground working on it.
Looking now, baby, see them rockets in the sky. Somewhere there's someone steady staring upwards as they die. Some folks is frowning, doubting, but we'd never play around. Spike a holy ball of fire from the heavens to the ground. Yes, we're looking for a crowd pleaser, rockets in the sky. Yes, we're looking for a crowd pleaser, lit up like the 4th of July. And deadly like a devil femme fatale. Got people across our nation screaming, can you hear us now? No stranger propaganda, we're all suckers for a show. Grab a weapon at the door and leave behind your moral code. Yes, we're looking for a crowd pleaser, rockets in the sky. Yes, we're looking for a crowd pleaser, lit up like the 4th of July. living through the haze. Seems history is ended, time to cash in those chips, but you ain't seen nothing yet. The fuse has just been lit. It's a road runner and a grabber out on a cruise. It's a working man, a rich runner, yeah, it's burning up the blue. She my kissing cousin, wild-hearted, but her aim is true. Top up window, flashing my baby's howling out